In this video, I'll explain how matched filters work both mathematically and intuitively. So, in a communication system, the received signal can be modeled as R of t is equal to S of t plus N of t, right? Where S of t is the transmitted signal and N of t is white Gaussian noise. In particular, additive white Gaussian noise. So you can imagine the useful signal we care about is buried inside this random noise. The noise is superposed on top of our transmitted signal and it's making it all fuzzy, right? So the purpose of a matched filter is to maximize this signal to noise ratio. And it wants to do that. It wants to maximize the signal to noise ratio, specifically at the sampling instant, right? So, intuitively, the matched filter behaves like a correlator, with the correlator formula being the integral from minus infinity to infinity R of t S of t with respect to t. That gives us our output. That gives us our output in time. So what this does is that it compares the received signal against the waveform we are trying to detect. So signals are often represented as voltages or currents. So for this received signal, it's either a voltage or a current. And for this transmitted signal, it's either, for this waveform waveform that we're trying to detect, S of t, it's also either a voltage or a current. And so when you have the two of them multiplied, whether it's voltage squared or voltage times current, you get something that is proportional to power, right? And since we're integrating over time up to the sampling point, this gives energy, right? Because E is equal to power times time. And we all know multiplication is the same as addition, and addition, that is from the integration. Integration is essentially just addition through very small steps. And so that is equivalent to energy. So the matched filter effectively accumulates the energy of signals. In fact, this should be, instead of minus infinity to infinity, this should be from 0 in time to t of s, just to be a bit more clear. So as I was saying, the matched filter effectively accumulates the energy of the signals that resemble the waveform it was designed for. So we can modify our waveform that we are trying to detect, S of t, and we can choose what sort of signal would be closest matched to our received signal. So out of a combination we may have, the signal that is most closely matched to that waveform will, by this definition, accumulate more energy because you are aligning both the received signal and the detected waveform, and that will accumulate the energy. So to physically, if the received signal closely matches the desired waveform, the accumulation becomes large, producing a strong output peak at the sampling instant. So to physically implement this correlation operation, we use something called correlation. Now the formula of convolution. Now the formula of convolution is y of t is equal to the integral of minus infinity to infinity r of tau multiplied by the impulse function shifted by tau with respect to tau. Now what is t, what is tau? Both are variables of time. They are two separate variables of time. Those are just used, tau is just a convention used for bookkeeping. It's just a separate way of saying time because t is already taken, as you can see here. So tau, for example, in the received signal, this just gives us a scalar. This gives us a value, some sort of amplitude, and that is scaled by the impulse at that specific time, shifted of course. So the impulse function is scaled by r of tau and is added, is shifted. H of t is the impulse response, and convolution simply slides the one function across another. So the matched filter, how it works, this is where the magic lies. It chooses its impulse response to be h of t is equal to s of t sub s, which is the sampling instant, minus t. So what does this mean? The impulse, the matched filter chooses its impulse to be the time reversed and time shifted version of the impulse, right? So time reversed and shifted to the sampling instant, meaning this causes the received signal to align constructively at the sampling instant, maximizing the output energy. So if we can apply this to our formula, we see that y of t is equal to the integral from minus infinity to infinity r of tau s of, because we're now, h of t is just the reversed time and time shifted. So when we apply that over to our convolution formula, we have s of ts, which is shifted, and then now for the time reversal, minus all of this, t minus tau, d tau. And so at t equals ts, the sampling instant, look what happens here. In the waveform that we're trying to detect, the one that we're essentially guessing, s of ts, if we expand it all out, ts minus t plus tau, at t equals ts, we get s of ts minus ts plus tau, which is just s of tau. So now what we have is just from our convolution function, we now get r of tau, s of tau, d tau. Now since there is no t involved, we can obviously change this to a t, makes no difference, because it's now the same thing. And you can see here that it's just correlation. When we set the impulse from convolution to the time reversed and shifted signal. So that is essentially it. The matched filter works by time reversing and shifting the desired signal so that at the sampling instant, matching parts align. In fact, once again, this is from 0 to ts. the signaling interval. Matching parts align constructively and maximize the signal to noise ratio.